we're going to start out with y prime plus y is equal to 1 on x squared plus 1. So with this problem, we have p of x is equal to 1, g of x is equal to 1 on x squared plus 1, and mu of x is equal to e to the e to the x. And so then we apply our theorem. Whoops, what am I doing? That's g of x. I'm sorry. I'm really kind of screwing up here. T squared plus 1 dt plus c e to the minus x. That's our solution. The only problem is now that we have this integral to solve. And initially I thought, well, I got a t squared in the denominator plus 1. Maybe I could try a substitution. And so I did a tangent, x equals tangent theta, and then dx is secant squared theta d theta, and then we have 1 plus tangent squared theta, but that's equal to secant squared theta. So we're left with an integrand of e to the tangent theta, and that doesn't help us any. We can't do much with that. In fact, if you look at examples where they solve it, this particular problem, they put you back into the form of e to the t squared plus 1. So it doesn't do us any good to go to that form to use a trig substitution. We're not gaining any benefit from that. So there's another approach we could try. We could use partial fractions. So we have t squared plus 1. Okay, how do we break that up? Well, we could say that's t minus I times t plus I. And that would be t squared plus ti minus ti minus I squared. But I squared is minus 1, and minus 1 is plus 1, and that's what you got. So we could use that to make partial fractions. So we have 1 over t plus I times t minus I is equal to a over t let's say t plus I plus b over t minus I. Now we multiply through by the denominator on the left side, and so we have 1 is equal to a t minus I plus b times t plus I. And we solve for a and b, the unknowns. So let's t equals 0. So we've got 1 equals minus IA plus b IB. Okay, so b equals 1 plus, well, you know what, actually, let's do this. Let's multiply through by I, and we have I is equal to minus I squared, so that's A minus B, and so A is equal to I plus B. Now, we have that one relationship. Now let's take a look at another case where t equals 1. So we have 1 equals a times 1 plus I, or I'm sorry, 1 minus I, minus I plus b times 1 plus I. But remember, A is equal to I plus B, so we have 1 equals I plus B times 1 minus I plus B times 1 plus I, and we just do the algebra. So we have 1 equals I plus 1 plus B minus IB plus B plus IB, and now we have that one cancel with this, and this cancels with that, and we have minus I equals 2B, and B equals minus I divided by 2. That means that A equals I plus B, so that's plus minus I over 2, which means that A is I on 2. So we have B, A equals I on 2, B equals minus I on 2. And now we can erase all this stuff. Now that we can separate these into two integrals. So now we have, let's give her a little more room here. So we got y of x is equal to e to the minus x multiplied. Now we got two integrals. We got x e to the t on, what did we have there? It was t minus I on 2, and that's minus, whoops, before I go that far, dt minus x e to the t plus I on 2 dt plus c e to the minus x. I think that's what I had. Just want to make sure that I got this right to make. All right. So let's look at this a minute. I can bring the I on 2 out. E to the minus x times I on 2 e to the t on you know what, I think I have this backwards here. That should be plus, whoops. And that should be minus. There, I think I had it reversed. So we have this dt on t plus I minus x e to the t on t minus I. That should work. That's what we've got now. Okay, so now we've broken it into partial fractions and simplified it a little bit. And if you notice, we really have something very similar to e to the t on t dt. And this is called the exponential integral, and it's a specific function of this integration. This is not something that can be done easily. In fact, it's something that you really need special techniques. And if you recall, we have, let's see, I gotta look at my notes 1 minute. If we use a u substitution, so let's say u equals t plus I, and du equals dt, we have e to the negative x I on 2, and so u minus I equals t, and we have therefore, we have x e to the u minus I on u du. And we could do the same for this. We'll say p equals t minus I, dp equals dt, and p plus I equals t. So we have e to the p plus I on p dp plus ce to the minus x. Now, what we have here is something a little bit more easily integratable, because e to the u minus I is equal to e to the u times e to the I. And e to the I, u is the variable. U is the variable, so e to the I is some value. It's a constant of some kind. And so we can use that fact. We can use that. And we have e to the negative x I on 2 e to the u on u e to the I du minus, this is an integral, minus e to the p, this is minus I, and e to the I, and that's on p dp plus c equals c e to the minus x. Okay, so now we can take those outside each integral. So we have this, e to the negative x, I on 2, e to the minus I, x, e to the u on u du, plus e to the I, e to the p on p dp plus c e to the minus x. Now we have this in a form that is just like the exponential integral, and it's not solvable, at least explicitly. Let's see if I have all my terms correct. Let's just check it through. You know what I got? I got wrong here. Have to be careful. This is where you can run afoul by little things like that. So now we have this solution in a form that can be dealt with. So let's now give us a little room. And rewrite our problem. Y of x equals e to the minus x times I on 2. And this is e the minus I x e to the u on u du plus minus e to the I x e to the p on p dp plus c e to the minus x. Okay, so far that is what we got. Now, what we do, it's actually there isn't really an explicit way of dealing with this. What we did with the Gaussian, remember what we did with the Gaussian, e to the minus x squared was equal to the sum of -1 to the n x to the 2n on, I think it was n factorial equals 0 to infinity. We'll do something like that with e to the x. So e to the u is equal to some infinite series. This is a Taylor series. And so on. Goes on as an infinite series. Let's say this is f, and so f prime is equal e to the u, f double prime equals e to the u, f triple prime equals e to the u, f fourth prime equals e to the u, and so on. And these will equal, now as you take each derivative, a term drops out, and so you have a1, 2 factorial, a2, 3 factorial, a3, 4a factorial, a4, 5 factorial, a5. And if you don't know how that came about, that's because each time you take a derivative, the variable goes down goes down by one order. And so eventually you get to the point where you have just the constant. You've isolated the constant. That's actually what makes this whole process work. And then you say, what happens when u equals 0? Well, e to the u is always 1. 1 equals a naught. 1 equals a1. 1 on 2 factorial equals a2. 1 on 3 factorial equals a3. 1 on 4 factorial equals a4, and so on. So you end up, and this is really 0 factorial, and this one is 1 factorial. And so we end up with a series e to the u equals 1 on 0 factorial plus x on 1 factorial plus x squared on 2 factorial plus x to the third on 3 factorial, and so on. This is the polynomial equivalent to e to the x. And it goes on infinitely. And then you can put that into a more compact form, which states e to the u equals the sum of n equals 0 to infinity of x to the n on n factorial. And that's the exponential function. And so we can substitute that into the integrand. Now that's what we've done before, and it works. We did that with that more complicated function, the Gaussian distribution. So now that we have this, we have an interesting situation, because after we erase the board, we have y of x equals e to the minus x I on 2 e to the minus I and we got this polynomial series all on x. Whoops. Right. It's such a pain in the neck to... This is divided by x, dx, and this is minus x n equals 0 to infinity p, let's say x to the n factorial on x dx. We forgot something here. Let's rewrite this a little bit. Again, you have to be careful. There we go. And I think this does it. And so what we end up with is this. And now there are various ways we can go with this integral. But what we're going to do is we're going to go like this. X equals I on 2e to the minus x times e to the minus I. You know what? This isn't needed anymore because we're already in the variable x. Okay. When we look at this, we have x to the n minus 1 on n factorial dx minus e to the I x to the n minus 1 on n factorial dx. And now we integrate. And this will be y of x equals I of 2 e to the minus x e to the minus I summation of, darn it. Okay. Summation of n equals 0 to infinity of x to the n on n times n factorial minus e to the I summation of x to the n on n factorial, n equals 0 to infinity, plus c e to the negative x. We can reduce this down. We can go y of x equals I on 2 e to the minus x, and we can say e to the I minus e to the I times n equals 0 to infinity x to the n factorial plus c e to the minus x. And we had a condition. Y of 0 equals 0. So we have the polynomial there. And if x is 0, that term is 0. So we have 0 equals c. So in the end, we have y of x equals I on 2 e to the minus x. And we can do a little algebra here. I don't know if this is really worth it, but we have 1 on e to the I minus e to the I. We have 1 minus e to the minus 1 on e to the I. So that becomes 1 minus 1 on e to the I. That's e minus 1 on e to the I plus 1. I don't know if that's any simpler than what we've got before, so I'm not gonna waste time with it necessarily. So we've got this problem now solved with a final outcome. Y of x is equal to, oh, I had it written up there. Why am I doing it again? Okay, let's just, so we have, with c equals 0, we have y of x equals I on 2 e to the minus x, e to the minus I minus e to the I times the summation of n equals 0 to infinity x to the n on n factorial, and that's it. And in the book, this is the solution to the integral that we had. So that's equal to, what was that integral that we started out with? We had e to the minus x e to the t on t squared plus 1 dt. So that's how they left it in the book, because they didn't want to go through the solution. But it wasn't obvious to me that c was 0 until you go through with the integrations. But this is actually a solution that'll work, and I don't know how many terms you have to carry this out to get a precise answer and what range. But if you carry it out many, many terms, you'll be able to, get the answers that you want from this solution. So even though it's not ideal and it's not explicit, not everything is perfect as you would like. There's another way of looking at this problem. And what am I doing here? I want to close that. And I just want to point out that when you look at one of these terms, you got the integral of this summation you could do it like this. This is 1 on x dx plus, and you know what, because we got x, we don't need this. Plus dx plus, and now you have n let's see, was it 1 or 2? I think it's, how did I do that? Here we go. Yeah, it's 0. And I did this, x to the n plus 2 over n plus 2 factorial dx. And that's how we dealt with it. And then this gives you ln x plus x plus, and then you have this summation oops, I think you know what I did. I messed up here. And then I think this is the solution. Oops. Something like that. And if you go to Wikipedia, you'll see that that's one of the solutions is in that form. I'm just going to give it a quick check and see what we got. Here we go, the exponential integral. Yeah, here we go. It's, yep. That's an answer that they give you. At least very close. It has the ln function. Their solution is some gamma plus ln x plus the exponential of x on 2 times, and that's kind of something that we had, -1. There's actually is a little different, but it's similar in a sense in that it's got these terms, and we've got something similar here. Although I think my solution's probably a little easier to understand. But anyway, without that, I think this is the solution that probably works the best. At least for me, it's a little more compact. We could call this, we could call this term alpha or something like that, and then we go, or I to 2 times e to the -1 minus I minus e to the I. That is equal to alpha. So we can then shorten the thing. We could say alpha e to the -x, and then the summation something like that. And it simplifies it a little bit if we call alpha this factor here. So that's an approach that you can use to solve that integral. But what I find interesting is that in the very early stages of this course that we've been looking at in Boyce de Prima, that they give this problem at all, because that it's not a trivial solution. It's not a trivial problem by any means. Maybe that wasn't the best example to start with, but it's in the book, and they give it as a problem. In fact, it's not even one of the advanced problems. It's problem number 9 out of 18. So it's unfortunate, but let's see. Use method of problem 17. Oh, I see. That's where that... If e of x is identically, g of x is identically 0. So I see where that other solution may have come from. Very interesting. Something I might have to work out at some point. Here, this is the problem that we already solved. So that one we already did. I'm not going to do this one again. This one, however, I don't think we looked at that one. Let's see. What they oh yeah, we did solve that one. We did solve that one. We did that. Okay, so we don't need to do that again. Here's one. Number 10. I'm using Boyce de Prima, by the way. Y prime plus 2 on x, y equals cosine x on x squared. That looks like it could be a pretty interesting problem. So let's go. So we have here, using our theorem, we have p of x is equal to 2 over x. G of x is the cosine of x on x squared. And the mu of x is equal to e to 2, 1 on x dx, and that's equal to e to the ln of x squared, and that's equal to x squared. So it wasn't as scary a problem as we thought it might be, because now with our solution, we have y of x equals 1 over x squared times x t squared cosine t on t squared dt plus c on x squared. And do we have an initial condition? Yes, we have y of pi equals 0. So this really simplifies matters. And we've got y of x equals, and if you know y equals sine theta dy equals cos theta d theta, so y equals cos theta d theta, the integral. So we have 1 on x squared sine theta, x, what am I doing? X plus c on x squared, and y of pi equals 0. So we have 0 equals 1 on pi squared times sine of pi, which is 0, plus c on pi squared, and c equals 0. So our solution is y of x, it's going to be really simple, equals sine of x on x squared. So that one wasn't so bad. It looked like it could be pretty involved, but it wasn't anywhere. The previous problem was a heck of a lot more difficult. So that's the correct answer. And I think we can push on. This was interesting. Let's look. Okay, let's look at the problem here. X, y prime plus 2y equals sine of x, and we have y of pi on 2 equals 1. That's our initial condition. So p of x, okay, now we're going to divide through by y. So we got y prime plus 2 on x, 2 over x, y equals sine x over x. And so p of x equals 2 over x. G of x is sine of x over, oops, what happened? Over x. And mu is equal to e x to 1 on x dx, and that's equal to e to the ln of x squared is equal to x squared. So now we just apply our theorem, y e of x for first order linear of this form, 1 over x squared, x, let's say s squared times sine s over s ds plus c over x squared. Okay. What we have here is an integration by parts. uv equals u dv plus v du. So let's choose u equals s, du equals ds, v equals, let's say, cos s, dv equals minus sine s ds, and so now let's take a look at our solution here. So we got s cos s equals minus s sine s ds plus minus, let's see, this is u dv, v du. Okay, so now this is equal to this. This is what we're trying to solve for. Plus, now this is going to be sine of s. And so our solution, s cos of s minus sine s, is equal to minus s sine of s ds, but we got that negative sign there, so we end up with sine s minus s cos s, and that's our solution. So now we can put that in for the integral. So y of x is equal to 1 on x squared times sine of x minus x cos of x plus c on x squared. And we had an initial condition of y on pi on 2 equals, what was it, 1? So we have 1 equals 1 on, okay, that's 4 on pi squared times, this is 1 minus 0 plus 4 c on pi squared, and we can pull that out. We've got pi squared on 4 minus 1 equals c. I think that works for us. And so we have y of x is equal to 1 on x squared times sine of x minus x cosine of x plus pi squared on 4 minus 1 on x squared. And let's check. I think that's the answer. No. It isn't. In fact, what did I say? Pi on 2, y of pi on 2. Okay, let's take a look at this again. Now we have the right answer up here. That's correct. So let's relook at this again. Okay. Now this is correct up here. So if y of pi on 2 is 1, okay, so this is 1 equals, now this is 1 on pi on 2, that's squared, so we have 4 on pi squared times, times 1 minus 0, because cos of pi on 2 is 0, plus, this is c on pi squared on 4, so that 4 goes up there. I think we had it right. Let's, maybe I was too hasty. Times 1 plus c, so that would be pi squared on 4, right? And that's pi squared on 4 equals 1 plus c, so pi squared minus 1 on 4 minus 1 equals c. That's what we had. Pi squared minus 4 on 4. And I don't see any other way. So y of x is equal to 1 on x squared sine of x minus x cosine of x what if I integrated wrong? What if I integrated wrong? All right. So we did UV. Okay, UV is, we chose V to be that, so the derivative of cosine of S is minus sine of S ds. Okay, so we have S cos S, all right, equals the integral of u dv, so that's S sine of S, but there's a negative sign there for dv, plus cosine, so that should be sine. This solution looks right. Okay, minus, and then because of the negative sign, we rearrange that order, and we put it into the integral, and that solution looks right. I can't see any other way. Yet the book has y equals sine of x on x squared. Now that's the first term. It's as if this term and that term canceled. But cosine of pi on 2 is 0. So anything multiplied by 0 is 0. It just doesn't make sense to me. It looks like I have the right answer. Let's see if I work that out in my notes. Sorry about this. I just don't like having an inconsistency with my book. Let's see. Here we go. All right. All right. We got this so far. All right, okay, my solution so far. Okay, yeah, this is the right solution. You know what? Maybe it wasn't. Oh, you know what I was looking at? Oh, God. I looked at the wrong initial condition. This is right for the initial condition. This is correct. But what if we were given this initial condition? Then we have something different. So if that's the initial condition that was given. So let's look at this. All right, so we have y of pi equals 0. Let's not think of that. Y of pi. So we have 0 equals 1 over pi squared times 0 minus pi times minus 1 plus c over pi squared. So we have equals 1 on pi plus c on pi squared minus 1 on pi equals c on pi squared. So it's negative pi. And I still don't get it. I still don't get it. Because it still doesn't work. It doesn't give us. All right, so let's put this in and let's see. Y times y of x equals 1 on x squared sine x minus x cos x minus pi on x squared. And that still doesn't give us the solution in the book, does it? I don't know why. Now this is correct. This is absolutely correct. Maybe I'm looking at the problem wrong. But let's see. Huh. 12. Oh, God. We had it right to begin with. I'm so sorry. So, we had it correct. So, we had worked it out correctly. So, the initial condition given is, all right, this is it. We had the whole problem right the first place. I was looking at the wrong problem in the book. You got to be careful of these stupid things. You have to pay attention to what you're doing. All right, so that's the initial condition again was given as y on pi on 2 equals 1. So then we have 1 equals, and that's 4 on pi squared times, this is 1 minus 0 plus 4 pi squared c, and we can pull that out. We've got pi squared on 4 minus 1 equals c, and that's pi squared minus 4 on 4 equals c, and we got y of x equals, we had it right, x squared sine x minus x cos x plus pi squared minus 4 on 4 x squared. And that's it. That's our solution. I apologize for, but in a way, working through the problem this way shows you the care that has to go into looking at the solutions, because you can get crossed up pretty quickly on simple stuff, minor things. But Yeah, that's it. That's why it's important to check, double check, triple check, make sure that you haven't got a sign somewhere wrong or other things. So there's a valuable lesson to be learned from that alone. So unless you're one of those crazy math whizzes that can see the answer in their head before they put pen to paper, you have to be careful. You have to work through using care. So there we go. And that was quite an answer. I like answers like this. They look sophisticated.